Welcome back, everyone, to Physics with Miss McQueary. Today's lesson is going to be dealing in part of our unit on Newton's laws of motion and forces, continuing today with forces and free body diagrams. So the primary objective today is not only determining the forces that are acting on an object, but also being able to draw those free body diagrams to help visualize what's going on. Remember, when we're dealing with forces, when we're trying to identify them, there's a couple of things that need to occur. The force needs to change the object's state of motion. Namely, it needs to accelerate it. And that's accomplished in a variety of ways. Either you are slowing down the object, speeding it up, or changing the direction of the object. For example, the force of the bat on the ball is changing the direction of the ball. And it might even change its speed. Kicking a soccer ball, for example, you are definitely changing direction if you're kicking it, and you're definitely speeding it up if it's originally at rest. The person who is stopping on the long jump is slowing down. Therefore, there is acceleration. And our rocket ship is accelerating, building up speed as it tries to break the Earth's atmosphere. So remember, if there's a force present, there has to be acceleration present. They go hand in hand. There's a couple words here that are going to try to give you a sense of whether or not something is actually accelerated or not. And those words are usually in word problems like at rest or constant velocity when things don't accelerate. Remember, constant means that it's not changing. And if your velocity is not changing, then you can't have an acceleration. So if that's the case, then all of your forces will be balanced and they'll cancel each other out, meaning that the net force is going to be zero. You can still have forces acting on an object. It's just that they're equal and opposite to another force. If something is accelerating, the key words to look for are accelerating, speeding up, or slowing down. That means you have an unbalanced force, meaning there is a net force, and our free body diagram will look just a little different than if everything was balanced. Now, the way we approach these when we're trying to solve problems is I call the toolbox method. Basically, we're going to give you 5 forces that are common forces you deal with on an everyday basis, and we're going to use those to help identify the forces present and how to draw our free body diagrams. They are as follows: gravity, the normal force, friction, a push or pull, and tension. Some of these we use more often than others. Anytime that you are near the Earth's surface, gravity is usually going to be present. Sometimes in a word problem, it might be disguised with the word weight. It's still the same thing as gravity, just displayed a little differently. Another thing to know about gravity is it's usually downward, or even better, is it's towards the center of the Earth when we're near it. Right? The normal force is probably a force you haven't heard of before. That's basically a force that is perpendicular to surface when you have direct physical contact. For example, this textbook. The reason why that textbook does not just sink through or accelerate down towards the table is because you have the normal force of the table pushing back on the book. Luckily, it's in equilibrium, so your textbook won't be moving. Your normal force can change if you're on a slope, for example, though, because remember, the word is not just up, it's perpendicular to the surface. So if you have something that's at an angle, then your normal force will be at an angle. Friction, which includes air resistance, is a force that opposes motion. So whenever you have something in motion, it will be in the opposite direction of the motion's direction. For example, look at those 2 guys here in the bottom. The first guy on top is pushing his cart to the right, so friction works against it, meaning it's going to push to the left. And then that's flopped in the bottom one. Push or pull is exactly how it sounds. Sometimes you might hear it called the applied force, which is also the same thing. Tension is something you probably haven't dealt with a whole lot, but you actually do on an everyday basis. That's when you have things like string or wires or cables or rubber bands. There's tension in that object. Depending on its elasticity, there can be more or less. So if there's going to be tension, there needs to be some type of rope or string involved to have that as one of your forces. Remember these because we'll be using these to build our free body diagrams. These free body diagrams are basically something that shows all the forces that are acting on your object. You start with your object in the middle with either a dot or a cube or a circle, and then you draw the forces acting outwards from that. We don't want to see any arrows going towards the middle. We want to see them going away from the middle. Another note when it comes to forces is that the units that you use for this are newtons, named after Isaac Newton, and the abbreviated version is N, kind of like I use kg for kilogram or L for liter. This diagram shows 4 forces acting on an object. Notice the object is in the middle, and we have our forces pointing outwards. In this case, if you're looking at it, you may notice also that those forces are equal and opposite to the force that's directly across from it, meaning this object will not be accelerating. It may be moving, it just won't be accelerating. Let's do a couple problems together. Consider a 9 Newton book that sits at rest on the table. 9 newtons is the weight. And we know that the net force is equal to 0 because they do tell us that at the bottom. So let's run through our steps of how to make these. First, we want to figure out what are the forces acting on the book. Remember from our list that we have several forces, 5. There are 2 that are present for this one, namely gravity and the normal force. Let's figure out the directions. Gravity usually works towards the center of the Earth, so it's pointing downward, and the normal force is perpendicular to the surface. This surface is flat, so the normal force will be going straight up opposite of gravity. Now comes the drawing part. Because there is no net acceleration, and because there is no net force, we cannot be accelerating. The 2 forces cancel each other out. So that means that the forces should be balanced. So let's go ahead and add in our drawing here. There's our free body diagram. Gravity goes down, normal force is up, and we know that those have to be equal in magnitude because there is no acceleration and no net force on that object. Example number 2, a free body diagram of a ball falling through the air, and it tells us specifically to ignore air resistance. If we were going to include air resistance, this would look a little different. So the forces that are acting on the book, based on the 5 we went over, there's only one of them, just gravity, because we're ignoring air resistance. If we didn't, we'd have to put friction on there as well. The direction of gravity is towards the middle of the Earth, so it has to be down. Now let's talk about the acceleration. We remember from a previous chapter that objects that are falling through the air without air resistance are absolutely accelerating. And we remember that number, 9.81 meters per second squared. Now, are those forces balanced or unbalanced? If you're accelerating, it should be unbalanced. There is more pulling you than there is resisting it. In this case, it's a very simple free body diagram. There's only one force to worry about, and there's no force that's acting against it. So we just have gravity pointed down. Problem number 3 involves a box being pushed to the floor, on the floor to the right, and we're going to ignore friction. So this must be on an ice rink or maybe on a perfectly frictionless surface out in deep space. Let's talk about the forces that are acting on the book. We have a couple of them. One of them is gravity. It's still pointed towards the center of the Earth. Or, for our deep space example, it's pointed towards something, right? Normal force is also opposing gravity because you do have a surface you're in physical contact with, so it will be pointing up. And there is a push because this is specifically you are pushed on the floor to the right, so we need to include that as a force. Remember, we could have also said applied force. These are the direction of our forces. You're pushing it to the right, gravity pulls you down, and normal force is going to resist gravity. Let's talk about acceleration. Is the object accelerating? Well, right now we have 2 forces that are opposing each other, gravity and the normal force, but the push is kind of left to itself. There's nothing that's working against it. So if there's nothing working against it, there is a net force, therefore there is a net acceleration. So yes, the object is accelerating. Last question, Are they balanced or unbalanced forces involved? Well, yes. If the object is accelerating, we know there has to be an unbalanced force. Here's our free body diagram. You can see that push is left unchecked by another force. We have two more examples when it comes to free body diagrams. Someone pushing a cart to the right and someone holding a backpack up by the strap. In the first example, we have the normal force that acts against gravity. And because the cart is on the level surface, normal force is going to be pointing straight up. And then we have the push that's facing to the right. In the second example, we notice that tension and gravity are equal and opposite forces because Emily's holding her backpack by the strap. If she was accelerating it in a direction either up or down, those arrows look a little different. For example, if she yanked it up and accelerated her backpack up in the air, then we have an applied force to worry about as well. If she allowed it to fall, maybe a little bit, but still holding on to it just a little bit, you'd have a larger gravity and a smaller tension force because those would not be equal and opposite anymore. After today's lesson, I hope that we can both determine all the forces acting on an object and draw the corresponding free body diagram. Until next time, see ya.